Hey guys, good evening, good evening. Just give me a second. Perfect. So, welcome back one more time to the Unacademy NEET English channel. I hope all of you are doing great. So, people, quickly let me know in the chats if all of you can hear me, if I'm perfectly audible and visible to everyone. Quickly let me know in the chats. Welcome back, guys. Welcome back. Welcome back. Welcome back. Wonderful. Perfectly. So, without wasting a lot of your time, let me give you the context of the class first. So, dear students, tonight, we are going to start a very fresh and amazing series basically. Right? This is the first session of the series. And in this particular session, which will be approximately for 2 hours, I'll be completing 2 of your chapters. One is your mole concept, and one more is going to be your atomic structure, right? So basically, I'll be focusing on the topics from which questions have been asked frequently from past 10 years in your NEET examination, basically, right? So these topics, short topics. The Josh has to be high, guys. Let me know quickly in the chats. Everyone. Yes, I'll be starting from basics only. I'll be starting from basics only. All perfect? All right, guys. I would want you guys to take a note of every single thing, okay? Whatever I'll be mentioning on the screen, please take a note of every single thing because every single thing is going to be very, very, very important as far as your NEET examination is concerned. Okay, and if you're not like the session yet, please do like the session. If you're not subscribed to this new amazing channel yet, I would want you guys to do that as well, right? Because you guys are my army from now onwards, and you guys have to lift this channel and make it #1 in the couple of days. Yeah, that's something which I'm expecting for sure for you. All right, guys. Just a second. Perfect then. So let's get going. Let's get started with the first chapter, that is your mole concept basically, okay? So we'll start with the mole concept. So people, the first concept which I'm going to deal with in the tonight's session, which I'm calling as concept number 1 from the chapter mole concept. Have a look exactly what I'm going to say. I'm damn sure every one of you would have heard about AMU, right? I'm mentioning a term over here, that is AMU. What is AMU all about? Let me tell you, this AMU, this is also called as U, or you can call it as D as well, right? So this AMU, it stands for the atomic mass unit. AMU stands for the atomic mass unit. This U, it stands for the unified mass. And this D over here, it stands for the Dalton. Now, what this AMU exactly is all about? Either you can call it as AMU, or you can call it as U, or you can call it as D, right? The choice is all yours. So people, this AMU is defined as 1/12 of the mass of carbon-12 atom. This AMU is defined as 1/12 of the mass of carbon-12 atom, right? Now, my dear students, there is one thing which I would want you guys to remember. Mass of one carbon-12 atom. Let me tell you, mass of one carbon-12 atom, that is equal to 1.99 into 10 raised power minus 23 grams, right? How do we define AMU exactly? AMU is defined as 1/12 of the mass of carbon-12 atom. The mass of one carbon-12 atom exactly is 1.99 into 10 raised power minus 23 grams. Now, if I divide this particular term with the number 12, I'll be exactly getting the value over here as 1.66 into 10 raised power minus 24 grams. And I can represent it in terms of Avogadro's number as well. It's going to be 1 divided by Avogadro's number. This is one very, very, very important statement which I would want you guys to remember from now onwards. So people, 1 AMU, or you can call it as 1 U, or you can call it as 1 D. AMU stands for the atomic mass unit, U stands for the unified mass, D stands for the Dalton. And how do we define it exactly? It is defined as 1/12 of the mass of carbon-12 atom, right? The mass of whole carbon-12 atom in grams is 1.99 into 10 raised power minus 23 grams. If you divide this whole term by the number 12, you'll be getting exactly the value of 1 AMU in grams as 1.66 into 10 raised power minus 24 grams. And you can write it in terms of Avogadro's number as well, which is 1 divided by Na, right? So if you ask me now what this AMU is all about, I would say this AMU, or you can call it as 1U, or you can call it as 1D, it is just the reference. It is just the reference. It is just the standard. It is just the standard, right? This AMU, or you call it as 1U, or you call it as 1D. It is just the standard with which we compare the masses of different atoms, basically, right? It is the standard, it is the reference with which we are going to compare the masses of different atoms. What is meant by that? Let me give you one simple example over here. For example, I'm writing a statement. Understand and analyze things. Let's say I'm writing a statement. Atomic mass of oxygen. Atomic mass of oxygen. What is meant by it? Atomic mass of oxygen means I am talking about the mass of one atom of oxygen. And let me tell you, the atomic mass of oxygen, as you all must be knowing, it is 16 AMU, right? It's 16 AMU. Can I say 16 AMU can be written as 16 multiplied by 1 AMU? Absolutely, we can do that, right? Can I just, instead of this 1 AMU, can I write 1/12 of the mass of carbon-12 atom? Absolutely, we can do that, right? Now, dear students, instead of this 1 AMU, can I write 1.66 into 10 raised power minus 24 grams as well? Absolutely, we can do that, right? Absolutely. Now, let's try to understand all these terms basically. I wrote a statement, atomic mass of oxygen. That means I am talking about the mass of one atom of oxygen. And one atom of oxygen has got the mass of 16 AMU. It means one atom of oxygen is 16 times heavier than 1 AMU. It means one atom of oxygen is 16 times heavier than 1/12 of mass of carbon-12 atom. Or you can say the mass of one atom of oxygen in grams is equal to 16 multiplied by 1.66 into 10 raised power minus 24 grams. I hope this is clear to everyone, right? Perfect. Let me take one more example. Let me take one more example so that you can understand it properly. Dear students, if I write a statement like this, I'm writing molecular mass. Let's say I'm writing molecular mass. Molecular mass of what? Molecular mass of, for example, ozone. Molecular mass of O3. What it means exactly? It means I'm talking about the mass of one molecule of O3, right? It means I'm talking about the mass of one molecule of O3. Now, if I need the molecular mass of O3, how exactly I'm going to get it? The sum of atomic masses. Oxygen has got the atomic mass of 16 AMU multiplied by 3. The value comes out to be 48. Either you can write AMU, or you can write U, or you can write D. Now further you can break this 48U like this. 48 multiplied by 1U, or you can say 48 multiplied by 1/12 of the mass of carbon-12 atom, or instead of 1U, you can write 1.66 into 10 raised power minus 24 grams, right? Now understand what I'm going to say. Molecular mass of O3. That means I'm talking about the mass of one molecule of O3, which is 48U. It means one molecule of ozone is 48 times heavier than 1U. It means one molecule of ozone is 48 times heavier than 1/12 of mass of carbon-12 atom. It means that one molecule of O3 has got the exact mass of 48 into 10 into 1.66 into 10 raised power minus 24 grams. Exactly, right? I'm sure it's clear to everyone. Now, what kind of questions can be asked from this AMU basically? That is the point, right? There is only one type of question that can be asked. And I would want you guys to remember, understand, how do we deal with that sort of question which is asked from this AMU concept. Yeah? So let's have a look exactly what kind of question is asked from it. Look at the question carefully. Carefully look at the question. Carefully look at the question. The question says, if 1U is defined as 1/24th of mass of carbon to the atom, then calculate the molecular mass of carbon dioxide on the new scale. Look at the question carefully. Look at the question carefully. Understand. See, how did we define 1U? How did we define 1 AMU? We defined it like this. 1U is nothing, it is just 1/12th of the mass of carbon to the atom. This is how we defined it, right? Now, as per question, how are we supposed to define it? As per the question, we are supposed to define this 1U, which I'm mentioning as 1U dash, we are supposed to define it as 1/24th. 1/24th of the mass of carbon to the atom. This is how we are supposed to define this 1U as per the question, right? Now, dear students, how to tackle this question? As per us, we know 1U is nothing, it is just 1/12th of mass of carbon to the atom. But as per the question, we are supposed to define it in a different way. We have to define 1U as 1/24th of mass of carbon to the atom. What do I need to calculate? I need to calculate the molecular mass of carbon dioxide on this new scale. On this new scale, which is given as per the question. What I'll be exactly doing, let me call this as equation number 1. Let me call this as equation number 2. Okay? I'm calling the first one as equation number 1. Second one I'm calling as equation number 2. Let me just divide the two equations. Let's see exactly what I'm going to get. Have a look. If I divide these two equations, I'll be getting 1U divided by 1U dash. That means I'm getting something like this. U divided by U dash is equal to U divided by U dash is equal to this mass of carbon to the atom, mass of carbon to the atom cancelled. Over here in the numerator, you got 1/12. In the denominator, you got 1/24. Let's do a bit of calculation here. It is just going to be U divided by U dash is equal. It's going to be 24/12. That comes out to be 2. So I must say U is equal to 2 times U dash. So dear students, I would want you guys to remember, whenever you see this sort of equation, whenever you see this sort of equation, the first thing which you'll be always doing, you'll be always getting the relation between U and U dash. This has to be always your first step. This is always going to be your first step. Get the relation between U and U dash. Okay? The way I did. Number 1. Number 2, since you got the relation between U and U dash, let's see now, what else can we do? Let's see exactly what else can we do. Have a look, guys. Understand what I'm going to write. What are we supposed to calculate? The molecular mass of carbon dioxide on new scale. So I'm going to write the molecular mass of carbon dioxide. Can you let me know the molecular mass of carbon dioxide on the conventional scale which we know? You can. I mean, we can. How do we get the molecular mass of carbon dioxide? Simple, the sum of atomic masses, right? See, atomic mass of carbon is 12 AMU. And how many carbon atoms we have? 1 carbon atom plus. Atomic mass of oxygen is 16 AMU. We have 2 oxygen atoms. Take the sum, get the value. The value comes out to be 44U. This is the molecular mass of carbon dioxide on the scale which we defined earlier, right? Which we defined earlier. But we are supposed to calculate the molecular mass of carbon dioxide as per this new scale. That means we are supposed to calculate the molecular mass of carbon dioxide not in terms of U, in terms of U dash, right? So you can write this 44U in this way as well. 44 multiplied by 1U, absolutely. Or instead of this 1U, you can just write 2 times U dash. The value exactly comes out to be 88 U dash. So this is something which we were supposed to calculate. Let me know once in the chats if all of you can solve this sort of a question if it comes in your exam. Quickly, everyone. This is the molecular mass of carbon dioxide as per the new scale which is mentioned in the question. Right? Quickly, everyone. Guys, I'll be teaching you everything. Not only the 50 topics, every single thing. Whatever concepts are important in the question, all those concepts I'm going to teach you. I mean, whatever concepts are important in a particular chapter, all those concepts with the problems, everything I'm going to do. Okay? Wonderful. Perfect, perfect, guys. So one more similar sort of question. Let's give it a try. Let me see exactly, can you solve similar type of question? This is one more type of question, right? Let's say exactly, can we solve the question based on the same concept? Look at the question carefully. If 1U is defined as 1/6 of the mass of carbon-12 atom, what will be the molecular mass of NH3 on this new scale? Let's do it in the similar way. Since we know 1U is equal to 1/12 of the mass of carbon-12 atom. This is something which we know, right? This is something which we know. Let's call this as equation number 1. As per the question is concerned, how we are supposed to define this U? We are supposed to define this U as 1U dash, that is 1/6 of the mass of carbon-12 atom. This is how we are supposed to define this U as per the question. Let me call this as equation number 2. I got two equations, 1 and 2. What is the thing which we are supposed to do basically? We are supposed to get the relation between U and U dash, right? So what exactly I'll be doing? I'll be dividing these two equations, absolutely. Just divide these two equations. It's going to be U divided by U dash is equal to, in the numerator you will be getting 1/12. In the denominator you will be getting 1/6. The value exactly comes out to be 1 divided by 2. So I must say U divided by U dash, its value came out to be 1 divided by 2. Or I can categorically say U is nothing, it is just U dash divided by 2. So basically I got the relation between U and U dash, right? I got the relation between U and U dash. Number 1. My first step is done and dusted, right? Now what will be my second step? The second step is simple going to be, we are supposed to calculate the molecular mass of NH3. Now write the statement. Molecular mass of NH3. Molecular mass of NH3 as per our scale which we know. How much that will be? It's going to be sum of atomic masses. Nitrogen has got the atomic mass of 14 since there is one nitrogen atom. Hydrogen has got 1 AMU, 3 hydrogen atoms. So the value comes out to be 17U. So we calculated the molecular mass of NH3 as per the scale which we know, right? Perfect, as per the scale which we know. But we have to calculate the molecular mass of NH3 as per the scale that is given to us as per the question. So basically we don't need the answer in terms of U. We are supposed to calculate the answer in terms of U dash. Correct? So what I'll be writing? I'll be writing 77 multiplied by 1U, and instead of 1U, sorry, not 77, it's 17, right? 17 multiplied by 1U, so you can write it as 17 multiplied by, instead of 1U, you can write U dash by 2 basically here. You can write U dash divided by 2. The value comes out to be 8.5 U dash. This is something which we were supposed to calculate. Let me know once in the chats if everyone is super duper clear with this particular question, with this particular concept. Let me know quickly, people in the chats, if every single one is clear with this particular concept. This was our concept number 1. This was our concept number 1. Now comes the concept number 2. But before talking about the concept number 2, let me know in the chats quickly if all of you are clear with the first concept. Quickly, everyone. Yes? Thumbs ups in the chats quickly, everyone. Wonderful. Wonderful, guys. Perfect. Let's move ahead and let's talk about the average atomic mass. Okay? This is again one more important concept from which questions have been frequently asked. Before starting this particular concept, if I ask you what isotopes are all about. What are isotopes? What are isotopes exactly? You must be knowing it's very simple. Isotopes are the atoms of same element which have got same atomic number but different mass numbers, right? You know it. Isotopes are the atoms of same element which have got same atomic number but different mass numbers. For example, let's say you have got the element X. This is the element X. I'm assuming this X has got 3 atoms. This element X has got 3 atoms which have got same atomic number, which I'm representing with Z, and different mass numbers. Let's say this is M1, let's say this is M2, let's say this is M3. Understand what I wrote. I told you I've got the element X. This element atoms basically which have got same atomic number but different mass numbers, right? Those atoms of same element which have got same atomic number but different mass numbers, we call these atoms as the isotopes, right? So basically, these are the 3 isotopes of the element X. These are the 3 isotopes of the element X. Remember, whenever element has isotopes, whenever you have got an element which has got isotopes, at that point of time, we calculate the average atomic mass of an element. Whenever the element has got isotopes, for that element which exists in the form of isotopes, we do not calculate the normal atomic mass for the element. We calculate the average atomic mass, which is represented by MAB. Now the point is, how do we calculate this average atomic mass? How do we calculate it exactly? In order to calculate the average atomic mass of this element, which exists in isotopic forms, we need one more term. We need the percentage abundance. We need the percentage abundance of these isotopes. What is percentage abundance all about? That's something which I'll let you know in some time, right? Just understand and remember what I'm saying. Have a look. We have got the element basically. This element is existing in the form of isotopes. Whenever element has isotopes, you will be calculating the average atomic mass of an element. And in order to calculate the average atomic mass of an element, what do we need exactly? We need the percentage abundances of its isotopes. And these percentage abundances will be representing with A, B, and C, right? If you got the percentage abundances of the isotopes, then you can make one simple formula to calculate MAB. It's M1 multiplied by A. It's going to be M1 multiplied by A plus M2 multiplied by B plus M3 multiplied by C divided by A plus B plus C. Divided by A plus B plus C. This is one simple formula which you guys are going to remember from now onwards to calculate the average atomic mass of an element which exists in isotopic forms. At the same time, take a note of one more thing. Do remember the sum of percentage abundances. Do remember the sum of percentage abundances of all the isotopes. Of all the isotopes of a particular element. Of a particular element, it's always going to be 100. That means I'm talking about this term, A plus B plus C. It's always going to be 100. Let me quickly summarize it. Whenever you'll find an element which exists in isotopic forms, for that element, you do not calculate the normal atomic mass. We always calculate the average atomic mass, right? In order to calculate the average atomic mass of that element which exists in the form of isotopes, what do we need? We need the percentage abundance of these isotopes. If you got the percentage abundance of these isotopes, then you can simply write a formula, M1A plus M2B plus M3C divided by A plus B plus C. The sum of the percentage abundances of all the isotopes of a particular element, that's always equal to 100, right? Let me give you one example so that you can visualize it properly. One example which by means of which you can properly analyze and visualize it. See guys, you must be knowing about chlorine. Very simple element, this is chlorine, right? Yes? You know, chlorine has got 2 isotopes. One is Cl35, one more is Cl37. Chlorine has 2 isotopes, one is Cl35, another one is Cl37, right? Now dear students, I told you whenever an element has got isotopes, what do we calculate for that element? We calculate average atomic mass, MAV, right? And in order to calculate the average atomic mass, what do we need? We need the percentage abundances, right? And let me tell you, the percentage abundances of this Cl35 and Cl37, it is 75 and 25% respectively. What does it mean basically? What does this 75% mean? It means out of the total chlorine which exists in the universe, since chlorine exists in two different atomic forms, Cl35 and Cl37, but 75% of the chlorine atoms will be present in the form of Cl35, and remaining 25% of chlorine atoms, they'll be present in the form of Cl37. What it means exactly? For example, let's imagine entire chlorine is present in this room. Let's imagine entire chlorine is present in this room. Okay? Now, let's imagine there are some 100 chlorine atoms in this room. Out of these 100 chlorine atoms, there will be some Cl35 atoms, there will be some Cl37 atoms. Out of those 100 chlorine atoms, there will be 75 chlorine atoms. 35 plus M2 is 37 and B is 25 and A plus B value, you know, that's nothing, that's 100. So when you solve it, the value comes out to be 35.5 AMU. So this is basically, this 35.5 AMU, what is it? It is not the normal atomic mass of chlorine. It is the average atomic mass of chlorine. It is the average atomic mass of chlorine, right? Is it buffering? Is it fine now? Can you give me some confirmation from the chats? Is it clear now? Is it fine? Just refresh once, just refresh once. All cool, right? All cool. Perfect? Perfecto? All right, guys. Now focus on the session now. Cool, perfect. All right. I'm going to give you one question. Let's see exactly whether you'll be able to solve that question or not. One very simple question I'm going to give you. Let me see if you can solve that question. Understand and give it a try. Let's say you've got a question on the same concept. The question is something like this. We have got the element magnesium, and this magnesium, for example, it has got 3 isotopes. Let's say one is your magnesium 24, one is your magnesium 25, and one more is your magnesium 26. Let's say you've got a question in which you are given with the element magnesium. This magnesium, it has got 3 isotopes. Now, dear students, the percentage abundance of this Mg24, for example, it's given to you. It's given to you as 79%. It is given to you as 79%. At the same time, the average atomic mass of magnesium, let's say it's also given to us as 24.31 AMU. I am supposed to calculate the percentage abundance of Mg25 and Mg26. These are the two things which I'm supposed to calculate. Can you give it a try? Can you give it a try? Let me make you understand the question once again. You have got the element magnesium, right? It has got 3 isotopes, correct? Perfect. Now, out of these 3 isotopes, I'm given with the percentage abundance of one isotope. And I'm given with the average atomic mass of magnesium as well. And I'm supposed to calculate the percentage abundance of Mg25 and Mg26. Can you try it out? Can you try it out? See exactly how you're going to solve this sort of equation if it comes. Understand properly. My dear students, few minutes back, I told you the sum of percentage abundances of all the isotopes of a particular element, that's always 100, right? I told you a few minutes back, the sum of percentage abundances of all the isotopes of a particular element, that's always 100. If the percentage abundance of the first isotope is 79, right? Let's assume the percentage abundance of Mg25 is X. It is X. So what will be the percentage abundance of Mg26? Isn't it going to be 100 minus 79 plus X? Right? Since you know, the sum of percentage abundances of all these isotopes is equal to 100. It has to be 100. And out of 100, 79 is the percentage abundance of Mg24. This has got X. So this has to be 100 minus X plus 79. So basically, the percentage abundance of the first isotope is 79, the second isotope it's X, and the third isotope it's 21 minus X when you solve it. Correct? And these percentage abundances, as I told you already, we represent them with A, B, and C. We represent them with A, B, and C. And this 24, I'll be calling as M1. This 25, I'll be calling as M2. This 26, I'll be calling as M3. Now, instead of this M average, I'll be writing M1A plus M2B plus M3C divided by A plus B plus C, which is always 100. This value has to be 24.31. Isn't it simple? Isn't it simple, people? Correct? Now, dear students, M1 value, that's 24. A value, that's 79. M2 value, that's 25. B value, that's X. M3 value, that's 26. C value, that's 21 minus X. Divided by A plus B plus C, that's 100, is equal to 24.31. When you solve this expression over here, you just got one equation which contains one unknown. So you'll be getting the value of X as 11. And what this X exactly was? X was the percentage abundance of Mg25. So you got the percentage abundance of Mg25. In the similar way, you can calculate the percentage abundance of Mg26, which is going to be 21 minus X, which is 21 minus 11. The value comes out to be 10. Let me know in the chats with the thumbs ups if you got this particular concept properly. Everyone quickly. Everyone. Let me know quickly in the chats if everyone got this particular concept. Everyone means everyone. Give me some thumbs ups in the chats quickly. Are you all clear with this concept? Will you be able to solve this this sort of a question if it comes in your exam? Some people are saying the video is lagging. I don't know exactly. I'm right now live from Bangalore office, right? Or maybe I can talk to the team afterwards, right? Like there is some issue if... Perfectly done. Wonderful. Wonderful, guys. Good job. Perfect. That means you're all clear, right? Perfect, perfect, perfect. Perfect, guys. Now let's move on then. If this concept is clear, let's move on to one more concept. What is that? That is a limiting reagent. One of the most important topics of your mole concept. Majority of the times, if the question comes, that will be from limiting reagent. And this is the concept which is involved in the majority of the physical chemistry chapters. If your limiting reagent concept is strong, that means you'll be doing good in your physical chemistry basically. Because this concept of limiting reagent, it's involved at many places in the other chapters of physical chemistry. Let's try to understand, let's try to analyze this limiting reagent concept properly. Yeah? Have a look now. So first of all, what this limiting reagent is all about. Let me keep it very simple and short and precise. Limiting reagent is basically that reactant. It is basically that reactant in a chemical reaction which is completely consumed. Which is completely consumed earlier in the reaction. What do we mean by this? I'm telling you, this is a very important concept, okay? Please and please have a look properly on this particular concept. Limiting reagent, it is basically that reactant in a chemical reaction which gets completely consumed earlier in the reaction. What do we mean by that? Have a look. To make you understand the concept of limiting reagent, I will be needing one reaction. Let's say the reaction is very simple like this. A plus B, it gives C plus D. Let's say it's a balanced chemical equation. Let's assume it's a balanced chemical equation, right? Now, dear students, if I say at time t is equal to 0, time t is equal to 0 means initial conditions. Initial conditions means the reaction has not started yet. Reaction has not started yet means there has been no product formation yet. There is no product formation yet. The reaction has not started. If the reaction has not started, that means the container in which this reaction has to take place, that container will be only containing the reactants. It won't be containing the products at time t is equal to 0. That thing should be clear to you, right? I'm saying at time t is equal to 0, the reaction has not started yet. If the reaction has not started yet, there would be no product formation in the beginning because the reaction has not started. These reactants have not reacted yet. So in the container in which the reaction has to proceed, in the container, you'll only find reactants. I'm assuming at time t is equal to 0, there are some 10 moles of A and there are some 5 moles of B present in the container. C will be 0, D will be 0 because the reaction has not started yet. Now, dear students, when the reaction will start, when these reactants will start reacting, what will happen? The number of moles of reactants will keep on decreasing. The number of moles of reactants will keep on decreasing. Now, that reactant among the two, which gets completely consumed, that too earlier in the reaction, that's something which you call as limiting reagent. Let's assume I took 10 moles of A, 5 moles of B. Now the reaction has started, right? Now the reactants have started reacting. The number of moles of reactants have started decreasing with time. Let's assume B is that reactant which got completely consumed. So I must say this B is the limiting reagent. It got completely consumed, right? After some time, out of 5 moles of B, there were 0 moles of B left in the container, right? Because I'm assuming this B is the limiting reagent. It got completely consumed. So out of 5 moles of B, there are 0 moles of B left in the container. Perfect. So B is my limiting reagent here. The other one is something which I'll be calling as excessive reagent. Excessive reagent. Excessive reagent is the one which does not get completely consumed in the reaction. That means out of 10 moles of A, there will be few moles of A left in the container at the end of the reaction, when the reaction would have stopped. There will be few moles of A left in the container at the end as well. And in the container, there will be some moles of products also, which would have got formed. Now the question comes. Calculate the moles of excess reagent left in the container. Calculate the moles of products which have got formed at the end of the reaction. That is the question which can be asked out of limiting reagent concept. Now, how to deal with this? How to deal with this concept? Understand what I'm going to say now. Now I'm going to tell you the types of the questions and the concepts involved. See, guys. First of all, what is the limiting reagent? Limiting reagent is that reactant in a chemical reaction which gets completely consumed. Okay. I assumed here B is the limiting reagent. That means it got completely consumed. The other one is excess reagent. There will be few moles of excess reagent left in the container. And when the reaction would have stopped, there will be some moles of C and D also present in the container at the end of the reaction. Correct? Now, people, let's say I've got a very simple question like this. The question is, I've got a reaction like this. N2 gas plus H2 gas, it gives NH3 gas. This is the reaction which I have. This is the reaction which we have, right? Let's say I'm writing at time t is equal to 0. Let's say I've got 10 moles of N2. I've got 10 moles of H2 as well. So there'll be 0 moles of NH3 formed, right? Because I'm talking at time t is equal to 0 when the reaction has not started. Correct? Now, dear students, do remember one important thing. Whenever in a chemical reaction, the amounts of all the reactants are given to you. Whenever in a chemical reaction, the amounts of all the reactants, which can be in terms of moles, it can be in terms of mass, it can be in terms of volume or whatever. Whenever in a chemical reaction, the amounts of all the reactants are given to you. At that point of time, you'll be using the concept of limiting reagent. Got it? When to use the concept of limiting reagent? When to use the concept of limiting reagent? When the amounts of all the reactants, which can be in terms of moles, which can be in terms of mass, which can be in terms of volume, when the amounts of all the reactants are given to us, use the concept of limiting reagent. Now, what are the steps to be taken care of? Remember, the first step always is to balance the reaction. The first step always is to balance the reaction. Is the reaction balanced now? Yes, the reaction is balanced. After balancing the reaction, since the reaction is balanced, now after balancing the reaction, just identify the limiting reagent. Now the point is, how do we identify the limiting reagent? It's very small. I mean, it's very simple basically. How do we identify the limiting reagent? One simple trick I'm going to tell you. Tell me how many moles of N2 we have. We have got 10 moles of N2. Tell me how many moles of H2 we have. 10 moles of H2. Correct? What is the stoichiometric coefficient of N2? It's 1 divided with 1. What is the stoichiometric coefficient of H2? It is 3. What is the value coming out to be from here? 10. What is the value coming out to be from here? 3.33. Which value is lesser? 3.33. The one which gets the lesser value, that will be always your limiting reagent. And the other one will be automatically your excess reagent. Perfect? Divide the given moles of reactants divide the given moles of reactants by their respective stoichiometry coefficients, the one which gets the lesser value, that will be always my limiting reagent. So this is H2 over here, which is my limiting reagent basically. Yeah, this H2 is my limiting reagent. Now, if H2 is my limiting reagent, just remove all the calculation which you have done. You have identified the limiting reagent, which is H2, correct? If H2 is the limiting reagent, that means it would have got completely consumed in the reaction. Out of 10 moles of H2, there will be 0 moles of H2 left in the container because it's the limiting reagent, completely consumed, right? Now, dear students, this is the limiting reagent. This is the excess reagent. That means out of 10 moles of excess reagent, there will be some moles present in the container. Similarly, when the reaction would have stopped, there would have been few moles of NH3 which would have got formed as well, correct? There would have been few moles of NH3 which would have got formed as well at the end, correct? Now the question is, which I'm asking to you, calculate the moles of NH3 formed. Let me know how many moles of N2 are present in the container. How you are going to get this particular information? It's again simple. Limiting reagent is the one which is going to let you know about this particular information. Do just one thing. Let's just relate the stoichiometry of limiting reagent with the stoichiometry of NH3. Let's relate these two stoichiometries. Can I say from the stoichiometry of the reaction, can I say 3 moles of limiting reagent gives 2 moles of NH3? This is something which we got from the stoichiometry of the reaction, right? 3 moles of H2 gives 2 moles of NH3. Now we use the unitary method. So 1 mole of H2 gives 2 by 3 moles of NH3. Gives 2 by 3 moles of NH3. Now people, if 1 mole of H2 gives 2 by 3 moles of NH3, how many moles of H2 we have? We have 10 moles. So 10 moles of H2 should give me 2 divided by 3 multiplied by 10. Value comes out to be 6.66. This is going to be moles of NH3. What is this term? What did I get? I got to know the moles of NH3 which have got formed at the end of the reaction. So I got to know, dear students, there are 6.66. There are 6.66 moles of NH3 which would have got formed at the end of the reaction. Correct? Now if I ask you, how many moles of excess reagent are left in the container? How many moles of excess reagent are left in the container? Limiting reagent is going to give you the idea about that as well. Limiting reagent is going to let you know how many moles of excess reagent will be left in the container. The point is how? Just relate the stoichiometry of limiting reagent with the stoichiometry of N2. So from the stoichiometry of the reaction, can I say 3 moles of H2 reacts with, I'm using the term reacts with, 3 moles of H2 reacts with, 3 moles of H2 reacts with what? Reacts with 1 mole of N2. Correct? I can say 3 moles of H2 reacts with 1 mole of N2. So can I say 1 mole of H2 reacts with 1 by 3 moles of N2? Absolutely. As per unitary method, 1 mole of H2 reacts with 1 by 3 moles of N2. So 10 moles of H2. So 10 moles of H2 would have reacted with 1 by 3 multiplied by 10. The value has come out to be 3.33 moles of N2. Tell me, what did we get? Tell me, what did we get? Can I say 3.33 moles of N2 have reacted with 10 moles of H2, right? With 10 moles of H2, 3.33 moles of N2 have reacted. How many moles of N2 did I take in the beginning? 10. Out of 10 moles of N2, I must say 3.33 moles of N2 have reacted. So how many moles of N2 will be left in the container? It's 10 minus 3.33, the value comes out to be 6.66. So people, it's 6.66 moles of N2 which will be left in the container at the end of the reaction. Is this concept clear to everyone? You got the moles of product formed when the reaction has stopped. You got the moles of excess reagent left in the container at the end of the reaction. Now you tell me whether you're clear with this particular concept or not. Quickly, everyone. Quickly. Everyone in the chats, quickly. Everyone in the chats, quickly, with the thumbs ups, yes. Quickly, guys, everyone. Let me quickly summarize now. Whenever in a reaction, the amounts of all the reactants are given, we'll be using the concept of limiting region. The first step which we always need to do in the limiting region concept is to balance the reaction. After balancing the reaction, divide the given moles of reactants by the respective stoichiometric coefficients. The one which gets the lesser value, that's always going to be the limiting reagent. And limiting reagent is the one which is going to decide the entire product formation. Limiting reagent is the one which is going to decide the amount of excess reagent left as well. Let's try to solve a few more questions and we can move ahead. Very simple and basic question. Very simple and basic question. You just have to identify the limiting reagent. The reaction is already given, and the reaction is given in the balanced format. 3 moles of NaOH. So I am given with 3 moles of NaOH. Reacts with 4 moles of H2SO4. 4 moles of H2SO4. So initially we have got 3 moles of NaOH. We have got 4 moles of H2SO4 as well. So this has to be 0. This has to be 0. Correct? If I ask you, oh, is it echoing? I don't know, guys. Sound not clear. Just a second. Is it fine now? Is it okay now? Nope. I don't know what to do, guys. Yeah, Reagent. This was not supposed to happen yet. Just a second. Let me call someone. Just give me a second, guys. Hello? Bro, there are some audio issues coming. Can you come in the room? Quickly. Guys, just give me a second. One guy is coming to help me out. Give me a second. He's coming up. Till then, you give it a try. Just a second. There are some audio issues, students are telling. Quickly. Guys, just a second. Audio. Guys, can you hear me now? Can you hear me? Can you hear me properly now? Is it okay? Is it okay? Is it all clear now? What's wrong here? Double audio is coming, is that? Is it fine now? Now all okay? All clear now? All clear? Yes, I think it's fine now. Is it okay now? It's not? Hello, 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 hello. Hello. Wait guys, just a second, the team is fixing it up. They're saying it's not. Press that, yeah. Hello, hello, hello. Guys, can you hear me now? Is it clear now? Something is wrong. Is it better now? Is it better? Is it better now? It's okay? Can you check from your phone once? All clear, guys? Yeah? Perfect. Okay, let's continue now. Be here only. Alright, I think everything is sorted here. Okay, let's move ahead. Alright, I'm continuing, guys. Okay, perfect. So in this particular question, what we are supposed to do, we are supposed to identify the limiting gradient, right? Same procedure I would want you guys to do. Same procedure. Since in this particular question, the amounts of all the reactants are given to us. And the amounts are given to us in terms of moles. Amounts of all the reactants are given to us, that too in terms of moles. Right? What is the first thing which we need to do? We are supposed to balance the reaction. The reaction is already balanced. Now identify the limiting gradient. Divide the given moles by the respective stoichiometric coefficients. That's it. So it's going to be 3 divided by 2, 3 divided by 2. It is 4 divided by 1, 4 divided by 1. This value comes out to be 1.5. This value comes out to be 4. Now, this is the lesser value, and the one which gets the lesser value, that's always your limiting gradient. So it's NaOH which is the limiting gradient in this question. Simple, basic, right? Let's have a look at one more similar sort of question. Let me see exactly if you can solve this question or not. Have a look. Have a look. The question is, I am given a reaction, and the reaction is something like this, which is given in the balanced form. 6 times LiH plus 8 times BF3, it gives 6 times LiBF4. LiBF4 plus B2H6. This is the reaction that's given to us. Correct? This is the reaction that's given to us. Now, my dear students, at time t is equal to 0 initially, how many moles of reactants are we given with? We are starting with 2 moles each of reactants. We are starting with 2 moles each of reactants. So how many moles of LiBF4 and B2H6 would have got formed initially? 0. Since the reaction has not started yet. The reaction has not... Wait, there is something wrong again here. I don't know what's wrong with the audio. Is it fine now? Is it fine now? Just a second, guys. Just a second, just be with me. Huh? Can you hear me now? Is it clear now? It has to be clear. Now it has to be clear, yaar. I think it is, yeah? They're saying no. Just wait a second, guys. I mean, the team is correcting it. इसकी सेटिंग सारी चेंज हो गई कैमरा की look from here. Wait. I think it's all clear now, right? Guys, tell me one last time, is it fine now? Everyone wants in the chats, everyone, quickly. Is it fine now? Guys, just be with me for 2 minutes. I'm really sorry about it. But the team is continuously, doing it, trying to fix it. Hello. Am I audible properly now? Hello. People are saying they can manage. Guys, can you manage for now? I'll get it sorted maybe tomorrow. Just tell me, can you manage for now? Alright, let me continue then, okay? I'll check it after at the end of the session because the time is running. I hope it's not that bad, yeah? Cool? Give me thumbs up once, everyone quickly. Give me thumbs up, everyone. Alright, I'll continue, okay? Let me continue. Alright, so basically, as far as this particular question is concerned, it is a similar question. We are given the reaction. We are given the amounts of all the reactants. We are supposed to calculate the moles of B2H6 which would have got formed at the end of the reaction. When the reaction would have got completed, we need to calculate the moles of B2H6 formed at the end of the reaction. Now, dear students, in this particular question, again, I'm given with amounts of all the reactants. So, I will be using the concept of limiting reagent. The first step in the limiting reagent concept is to balance the reaction. It is already done. The reaction is balanced. Now, identify the limiting reagent. How exactly? Divide the given moles by the respective stoichiometric coefficients. So, 2 divided by 6, similarly 2 divided by 8. The one which gets the lesser value, 2 by 8 is less than 2 by 6. So, BF3 has to be your limiting reagent. So if BF3 is the limiting reagent, that means out of 2 moles of BF3, there will be 0 moles of BF3 left in the container at the end of the reaction, right? Now the entire product formation will be decided by this BF3. Entire product formation. What are we supposed to calculate? We are supposed to calculate the number of moles of B2H6 formed. Correct? How do we get it? Just relate the stoichiometry of the limiting reagent with the stoichiometric coefficient of B2H6. Limiting reagent is the one which decides the entire product formation. So I am relating the stoichiometry of the BF3 with this B2H6. Have a look. It's 8 here. It's 1. Can I say from the stoichiometry of the reaction, 8 moles of BF3, it gives 1 mole of B2H6. Right? 8 moles of BF3 gives 1 mole of B2H6. So that means 1 mole of BF3 will give 1 divided by 8 moles of B2H6. Correct? So if 1 mole of BF3 can give these many moles of B2H6, what about 2 moles of BF3? 2 moles of BF3 can give 1 divided by 8 multiplied by 2. The value is 1 by 4, which is basically 0.25 moles of B2H6. So you got to know at the end of the reaction, 0.25 moles of B2H6 would have got formed. Is this clear? Is it clear to everyone? Guys, I think the voice is not clear. Let me repeat the session from here in the next session, okay? Because a lot of students are saying, I'm really sorry about it. I was not expecting this to happen in the first session only. So, let me tell you, it's completely okay. Just a second, it's completely okay. See, tomorrow my schedule was basically, which I had planned, that was redox. That was redox plus states of matter, the gaseous state. Redox plus gaseous state. Okay, but I'll be adding whatever left out topics are there in the today's session. I'll be adding those left out topics also, right? So I'll be doing it at tomorrow 8 p.m. I'm really sorry about this since there is a technical glitch, right? Okay, right? Okay. I'm trying to fix it. Basically, the team is here. They are continuously fixing it. They are unable to find the issue. It's some tech issue, basically. I don't know what exactly it is. But you be relaxed. Whatever are the left out topics, right? In the today's session, I'll be starting the tomorrow session with the same left out topics. You don't worry about it, okay? Is that fine? All right. Guys, tomorrow at 8 p.m. Tomorrow at 8 p.m. I'll continue from the same topic, from the same limiting reagent concept only, right? Because the team is continuously working, they are unable to find the issue. I don't know what exactly is wrong. I'm really sorry about it, okay? I was not supposed to, I was not expecting this to happen in the first session, but it happened. It's okay completely, but I'll make sure that I'll do it in the tomorrow session. Okay? Take care. God bless you all.